Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 12, 2026, just 2 days ago. It reveals a startling vulnerability in modern AI, showing that state-of-the-art models suffer a catastrophic performance drop of up to 80% when faced with irrelevant context or distractors. The paper is titled, Lost in the Noise: How Reasoning Models Fail with Contextual Distractors. And as we'll see later, the proposed solution offers a really promising path toward making agentic workflows much more robust. Figure 1 visualizes this vulnerability by contrasting traditional methods with the new NoisyBench framework. The top blue panel displays clean benchmarks, where agents receive sterilized context and easily succeed. In contrast, the bottom beige panel reveals what happens when realistic noise enters the pipeline. For example, on the far right, a hard negative distractor completely misleads a retrieval-augmented generation system. Similar failures occur with random documents and irrelevant chat history, showing that agents often get confused and output incorrect responses when the input is not perfectly clean. Table 1 quantifies this impact across 11 datasets covering RAG, reasoning, alignment, and tool usage. The table lists 7 major models, evaluating each under 4 conditions: no distractor, random documents, random chat, and hard negatives. Looking at the top block, Gemini 2.5 Pro starts with a strong 78% average in the clean setting. However, facing hard negative distractors, its performance crashes to 48%. Further down, the smaller DeepSeek R1 Distill Llama 8B essentially collapses, suffering an 80% relative drop to single-digit accuracy, which proves that even powerful reasoning models can be easily derailed by misleading context. So, while Table 1 focused on raw models, Figure 2 asks if agentic workflows, where models use tools, can solve the noise problem. The top left panel confirms that in clean settings, agents do improve performance, with the striped bars generally beating the solid base model bars. But look at the bottom right panel for hard negatives. Here, and in the other noisy settings, the trend reverses and agents actually perform worse. This happens because agents tend to overtrust the distracted tool outputs, propagating errors rather than fixing them. Given those failures, Table 2 asks if better training can help. It compares strategies like prompting, supervised fine-tuning, and reinforcement learning across 3 models. Surprisingly, the supervised fine-tuning rows in the top block show that this method often degrades performance, causing a 40% drop in the random document setting due to catastrophic forgetting. However, the method labeled RL with outcome reward plus rare changes the game. By rewarding the reasoning steps directly, it achieves a 55% improvement in that same setting. Well, Figure 5 digs deeper into the underlying failure mode by plotting accuracy and effort against distractor similarity. Across datasets like BBQ and Musique, we see a consistent inverse relationship. The red accuracy line steadily declines as the distractors become more similar to the question, moving from bin 1 to bin 5. Conversely, the blue line shows the average number of reasoning tokens skyrocketing. This reveals that similar distractors actively confuse the model, which burns more compute trying to resolve the ambiguity but still gets the answer wrong. To understand the source of that confusion, Figure 8 peers inside the model's attention mechanism. This plot compares the total attention mass assigned to distractors for incorrect answers on the left versus correct answers on the right. The dark green box for the distracted cases sits significantly higher, indicating that when the model fails, it is heavily focusing on the noise. In contrast, the lower light green box shows that correct answers correlate with suppressed attention to distractors, confirming that robustness depends on ignoring irrelevant input. Wrapping up, 2 takeaways stand out. First, exceptional scores on clean benchmarks do not translate to robust real-world agents, especially since tools can amplify errors. Second, the rationale-aware reward method demonstrates that to build resilient systems, we must train models to explicitly filter out noise rather than just focusing on the final answer. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.